So here in our second video, we're going to continue our discussion of the climatology of the tropics by taking a look at our major tropical circulations in three dimensions, horizontally as well as vertically, as well as atmospheric structures of things like not just temperature, as we looked at before, but only at the surface, but throughout the troposphere, temperature, moisture, and to a lesser extent, wind. So here we're going to start at 200 hectopascals, so very near to the tropopause during southern hemisphere summer. So this would be during our winter, so we can think about this as occurring during the January period. So here in the southern hemisphere, what we will more generically call the summer hemisphere in this case, we see anticyclones over Africa, Australia, and South America, keeping in mind that these are associated with counterclockwise rotation in the southern hemisphere. So these streamlines with the arrows that you see along them give us a measure of the wind direction, and how tightly packed they are give us a measure for how fast the wind speed is. So we see in this case anticyclonic or counterclockwise rotation over the land masses. Whereas here over the southern Indian, but especially the southern Pacific and southern Atlantic oceans, we have mid-oceanic troughs near the tropopause associated with clockwise or cyclonic rotation here in the southern hemisphere. In the northern hemisphere, it's winter, and we're not going to pay much attention here, but I will point out this very fast Pacific jet that extends from west to east from Asia toward North America with very fast wind speeds here to the east of Japan. So you might be asking, why do we see these anticyclones over land here in the summer and these cyclones or troughs over water during the summer? So we can relate this back to the properties of land versus water as well as thickness. So land heats up and cools down much more rapidly than does water. It has a lower specific heat capacity, which allows it to be more responsive to a given amount of energy that is input into it. So as you get into the summer, land is relatively hot compared to water. It's not that the water is cold by any means, but we're looking at something like 90 degrees Fahrenheit versus 80 degrees Fahrenheit. This leads to land having higher temperature and so greater thickness than does water. And so consequently, if we're looking at the top of that atmospheric column, we would expect that to be higher up. So higher heights, higher pressures in the upper troposphere over land where it's relatively warm, and lower heights, lower pressures in the oceans where it is comparatively cold. So we'll see this pattern hold true as we get to the northern hemisphere summer in a couple of slides here, but keep in mind, upper troposphere, hot land, anticyclone or high aloft, water, relatively cool, cyclone aloft. If we take a look here near the top of the boundary layer, 850 hectopascals, so roughly 1 to 2 kilometers above the surface, we see that pattern that we saw at upper levels flip. We have a heat low here over southern Africa where we had an anticyclone before. So this can be explained using thickness arguments once again, but instead of looking at the top part of the column, we're now looking at the bottom part of the column. We're pushing that down, so we're bringing lower pressures down toward the surface where it is relatively hot. So we get this heat low here associated with clockwise rotation over this very strongly heated landmass. We also have cyclonic circulation here over northern Australia and extending to the southern portions of the maritime continent, associated with what we call the Australian monsoon. If we look out over the oceans, however, we see this amplified subtropical ridging. In both the northern and the southern hemispheres, the winter and the summer hemispheres in this case, we see anticyclonic flow, counterclockwise in the southern hemisphere, clockwise in the northern hemisphere. But it's stronger in the summer hemisphere, noting the greater packing to the streamlines here over the southern Pacific and southern Atlantic than we see in the North Atlantic and the North Pacific. We also see this amplified subtropical ridging here in the southern Indian Ocean as well. We have flow coming clockwise around these anticyclones in the northern hemisphere and clockwise or counterclockwise around them in the southern hemisphere, giving rise to our easterly convergent trade winds near to the equator in both the Atlantic and the Pacific Oceans, to lesser extent here in the Indian Ocean because of the different land versus water contrasts that we see there as compared to the Atlantic and the Pacific Oceans, which are more water in both hemispheres. So whereas in the upper levels we saw anticyclones over land and troughs or cyclones over water, here near the surface we see cyclones over land and anticyclones over water. As we go to the northern hemisphere, our summer, so southern hemisphere winter, we can think of this as July, give or take. We see the same types of patterns at 200 hectopascals as we saw in the southern hemisphere. We have this very intense anticyclone here over the Middle East into Southeast Asia, associated with what we call the Indian anticyclone or monsoon gyre. We also see an anticyclone here over North America. You can see one here on the far east edge of the map in Western Africa. Likewise, we have troughs in the middle portions of the Pacific and the Atlantic Oceans here. Whereas we have a very strong jet extending across the entirety of the globe in the winter hemisphere down in the southern hemisphere. So again, anticyclones over the strongly heated land masses, troughs over the relatively cool waters near to the tropopause. Then we go to 850 hectopascals, that pattern flips once again. Anticyclones over the water. Here we have very strong anticyclones, areas of high pressure in the North Pacific and North Atlantic Oceans. Again, we see them in the winter hemisphere as well, but they are not quite as strong as we see in the summer hemisphere, given the stronger packing to the streamlines that we see here, especially with the easterly flow on the south side of each of the high pressure systems. We have our easterly trade winds blowing from east toward west in the Atlantic and in the Pacific near the equatorial regions, with the flow converging from the southern and northern hemispheres into these trade wind regions. Here over the Indian Ocean and extending from Australia and the maritime continent into Southeast Asia, we have what is known as the Indian or Asian monsoon. Here we have flow coming from the south in the southern hemisphere, curving around from the southeast to the southwest as you go across the equator, and then spiraling into this area of cyclonic rotation near to the surface, centered somewhere near Africa and the Tibetan Plateau. You get this very strong heating of that elevated landmass that gives rise to this area of low pressure that we call the Indian or Asian monsoon. And the flow coming in there spirals around the equator as you go from one Coriolis force sign, negative, to another, positive, here in the northern hemisphere. We'll talk a lot more about monsoon circulations, both the Indian and Asian monsoon, as well as the weaker monsoons of Australia, North America, South America, and Africa, as we get another several weeks later on in the semester. So now we've taken a look at two different levels, one near the surface and one near the tropopause in terms of the horizontal flow. Now we want to look at the vertical flow between those surfaces. We start here from January through March, so this is mostly southern hemisphere summer into the very early portions of southern hemisphere fall. We have January, February, March, and what we have depicted here is the pressure vertical velocity, or omega. So this is a change in pressure with time, and since pressure decreases going up, upward motion is associated with negative change in pressure, which means that negative values indicate ascent. So that's what we see depicted here in the blue and purple here in the southern hemisphere, especially from the equator to about 15 degrees south in January and February. Whereas descent, air going downward, is associated with positive values as it's going toward higher pressures as you go down toward the surface. And that's what we see in the northern hemisphere here, especially between 10 and 30 degrees north latitude. So here during the southern hemisphere summer, that region of maximum ascent is located preferentially on the south side of the equator, but still firmly within the tropics, with descent across much of the northern hemisphere tropics and subtropics. As we go from January to March, the region of ascent contracts somewhat, especially on its southern end, and the region of descent becomes somewhat weaker here, especially as you go from February into March. If we move to April to June, so this is our transition period from southern hemisphere summer toward northern hemisphere summer, our descent in the northern hemisphere completely goes away from April to May and into June. Whereas we get descent developing in the tropics and subtropics in the southern hemisphere from April to May to June, such that June looks a lot like January did, just flipped between the hemispheres. This region of ascent crosses the equator as you go through April and becomes centered between about the equator and 10 to 15 degrees north latitude by the time we reach June, whereas descent extends from about 7 degrees south all the way through 30 degrees south by the time we reach June. So this is flipping the pattern as the seasons evolve. Now as we go from July through September, the core of northern hemisphere summer into the early part of northern hemisphere fall, we see that the region of ascent is fairly consistent between the equator and about 15 degrees north latitude. The region of descent is fairly consistent, especially in July and August, but then weakens and contracts somewhat as you head in toward September. And then likewise, as we go to October to December, descent develops once again within the northern hemisphere, north of about 10 to 15 degrees north latitude. The region of ascent moves southward once again toward the equator as you go toward southern hemisphere summer. And the region of descent in the southern hemisphere goes away completely from October to November to December. So we get this moving region of ascent, or what we will define as the ascending branch of our Hadley cell circulation that we'll talk more about in subsequent lectures. It's wherever summer is presently found, or close to wherever the sun is most directly overhead during a given point in the year. It's in the southern hemisphere when the sun is directly overhead south of the equator. It's near the equator when the sun is nearly directly overhead the equator. And it's in the northern hemisphere when the sun is directly overhead north of the equator. Descent is particularly strong in the opposite hemisphere. So wherever it's winter, you have strong sinking motion. So this movement gives rise to the differences between our monsoon rainforest and wet dry climate classifications. Very close to the equator, you're usually in a region of ascent. So you're going to have rain throughout the year more often than not. However, as we've seen in these diagrams, the southern hemisphere and the northern hemisphere, north and south of about 10 degrees latitude, are sometimes in regions of ascent and sometimes in regions of descent. And so consequently, we get more of those wet, dry seasons where it's wet during the summer and dry during the winter as you get poleward of 10 degrees north and 10 degrees south latitude. We can see this manifest in terms of long-term averages of daily precipitation here. So these are shaded per the color bar that we see here in terms of millimeters for any given day. So 10 millimeters equals a centimeter, 25 millimeters equals about an inch. So that gets us into the reds here. So you're generally looking at about 1/3 to an inch of precipitation per day on average, wherever you're getting into the greens, yellows, and oranges within these diagrams. Here we're looking at January through March, which is primarily southern hemisphere summer. We see that near the equator, you can draw a nearly continuous line all the way across the globe where it is relatively moist. However, the heaviest rainfall is skewed slightly to the south of the equator. Here in southern Africa, the southern Indian Ocean, the maritime continent, and in the southern Pacific Ocean, as well as South America here. These bands of precipitation that you see in the ocean regions in particular are associated with what we would call convergence zones, where the flow converges from the north and from the south toward a given location. I guess from your point of view, since it's flipped from my camera, from the north and from the south in terms of easterly trade winds. The generic name is the Intertropical Convergence Zone. In the tropics, converging, a zone where the winds converge within the tropics, generally coming from outside of the tropics into the tropics and converging to a given location. They have specific names within several of the ocean basins, in particular the Southern Pacific, where it's known as the South Pacific Convergence Zone, as well as the southern Atlantic, where it's known as the South Atlantic Convergence Zone. We also see heavy rainfall maximized over South America, over Africa, and in the maritime continent. And these are associated with monsoonal circulations, of which the Australian monsoon is pointed out here, but you'd also have the South African and South American monsoon circulations. Whereas as we go to July to September, so the core of Northern Hemisphere summer into the early part of Northern Hemisphere fall, again, if we draw a line along the equator, we see that rainfall is generally relatively high everywhere along the equator throughout these months. However, rainfall is particularly maximized north of the equator, especially here over Southeast Asia and into the western North Pacific, as well as here in the western portions of the Atlantic Ocean, the Caribbean Sea, just off of the coast of Mexico and Central America as well. We see rainfall maximized associated with monsoons once again. The Asian or Indian monsoon are particularly noticeable here. To a lesser extent, we can see the North American monsoon, this heavier rainfall extending toward the desert southwest of the United States in July, August, and September, as well as this maximum right along the coast of Africa here, associated with the Western or North African monsoon. We also have our intertropical convergence zone, this band of heavier rainfall that is found just slightly to the north of the equator in the Atlantic and the Pacific Oceans here. So this region, this intertropical convergence zone, or ITCZ, tends to move with that mean region of ascent that we took a look at several slides prior. Slightly north of the equator in Northern Hemisphere summer, slightly south of the equator in Southern Hemisphere summer, with additional contributions from monsoon circulations that drive heavier rainfall during the local summer months over land masses in both the Northern and the Southern Hemispheres. So from here, we want to pivot a little bit to take a look at the vertical structure within the tropics. So not just surface temperature and not just kinematic fields, but we want to take a look at thermodynamic fields, temperature and moisture as well. So because of that net annual surplus of radiation that we described in our previous lecture, the tropics are the warmest region on the planet, on average, again, over the course of the entirety of the year. So from thickness arguments, again, we know warmer column leads to larger thickness, which pushes the tropopause to higher altitudes within the tropics. So that's what we're taking a look at here in the diagram at left. We have height above sea level here on the y-axis from 0 to 30 kilometers. And we have temperature from about -75 to +25 degrees Celsius here along the x-axis. So the tropics in this red line here start out and remain at the warmest temperatures throughout much of the troposphere. However, they do not begin to increase once again until you reach between 15 and 18 kilometers above sea level. So this region where the temperature begins to increase again with height is where we would define the tropopause to be. So again, between about 15 and 18 kilometers. Whereas in the mid-latitudes, given by the green line here, or the polar regions given by the blue line here, you see a similar decrease in temperature with height in the lower to middle portions of the troposphere. However, the tropopause is found at much lower altitudes, typically 9 to 12, 9 to 15 kilometers above sea level in the polar regions, sometimes even lower, and then between about 10 and 15 kilometers above sea level here within the middle latitude regions. And so the polar stratosphere here in the blue is actually warmer on average than is the mid-latitude and the tropical stratosphere, at least in this very basic conceptualization. If we take a look at a tropical profile here from St. Helena Island in the tropical South Atlantic, so this is in the far southeastern portions of the tropical South Atlantic basin here. We see that our tropopause is found very high up, in this case very near to 100 hectopascals. So we have a very deep troposphere here from the surface to about 100 hectopascals, with the stratosphere found above that. And this is a lot higher than we often see in the mid-latitudes, where during the summer it's closer to 200, maybe 250 hectopascals. In the winter it can be 300, 350, or even 400 hectopascals at some times. So we come down here toward the ground, however, we see a sharp separation between what we call the boundary layer, or the portion of the atmosphere that is in contact with the lower boundary or the ground, and the free atmosphere, the portion of the atmosphere that is free from the boundary's influences, especially from surface friction. And this feature that we see here separating those two regions where temperature rapidly is increasing with height is known as a temperature inversion. And in particular, this is a subsidence inversion. So once you get away from the equator, that region of mean ascent, there's typically weaker ascent north and south from there. And in some portions of the year, as we've described, there's even very strong descending motion. So subsidence inversions form due to that very strong descending motion. And they are common features of the subtropical to northern and southern portions of the tropics within the northern and southern hemispheres. They have a specific name associated with them called trade wind inversion because they are typically found in conjunction with those easterly trade winds near to the subtropical high pressure systems. We'll talk a lot more about those as we get another 6 or so weeks out into the semester. Now we want to focus a little bit more closely on the tropical North Atlantic here. So here we have a depiction of relative humidity from 1,000 up toward 0 hectopascals. And here we have water vapor mixing ratio in grams per kilogram over that same vertical region. We have two different data sets, one given by the gray line and one given by the black line. And they agree very closely with each other. Very moist conditions, high relative humidity, high mixing ratios within the boundary layer. But then as you get about a kilometer and a half up, you start to decrease the relative humidity and have a somewhat sharper decrease in mixing ratio as you go upward with height. In general, however, the tropical troposphere is very moist. Moist near the surface and somewhat less so as you get above the boundary layer. So there are three major air masses that influence the North Atlantic tropics. And one could say that two of these, the first and the third, also generally hold true for the Pacific Ocean, as well as the southern hemisphere, Pacific, Atlantic, and Indian Oceans. The second one of these is more specific to the Atlantic Ocean, as we'll talk about here in just a moment. So our first one is moist tropical, or MT, and this is about 2/3 of the air masses that we find within the North Atlantic tropics. These blue lines that you see here that look a lot like blue spaghetti are back traces. Where did the air at particular locations here in the western tropical and subtropical Atlantic originate from several days prior? And a lot of these lines overlap between about 10 and 20 degrees north latitude in the Atlantic Ocean. So these predominantly originate in the deep tropics and subtropics. They're typically warm and very moist throughout much of the troposphere. Our second one is the Saharan air layer, or SAL, which is about 20% of our air masses in the North Atlantic tropics. These are given by the red lines that you see here in the middle panel. These originate over the hot, dry soils of the Sahara Desert and then are transported primarily to the west across the tropical North Atlantic basin. This air mass is predominant during late spring, summer, and early fall when the Sahara is most strongly heated as the sun moves more directly overhead the Sahara Desert. You get very strong heating that generates a lot of turbulence, a lot of vertical mixing of air, extending up several kilometers, a few miles away from the surface. The easterly trade winds that we see over Africa tend to push this air out toward the ocean, where it becomes somewhat elevated above the boundary layer that you see over the oceans. So these are very dry air masses, especially into the middle portions of the troposphere, and that dryness originates over northern Africa. Our third air mass is this mid-latitude dry air, or MLD air mass. It's about 14% of our air masses in the North Atlantic tropics. These are given by the brown lines that we see here in the lower diagram. These generally originate in middle and higher latitudes, and they curve kind of in a clockwise fashion, anticyclonically. So they tend to come around the north and east side of an area of high pressure and hook into, I guess, this from your point of view. They come around the north side of an area of high pressure and then hook into the tropics on its east side. So these are also drier air masses associated with the typically drier conditions of the mid-latitudes, but with somewhat distinct characteristics from the drier Saharan air layer air masses, as we'll talk about in just a moment. So finally, we take a look at the mean soundings of the North Tropical Atlantic here. And we have 6 variables. Temperature in the upper left, so we see all of our lines are very similar, so we're not going to pay a lot of attention to this moving forward. We have relative humidity in the top middle, water vapor mixing ratio in the top right, equivalent potential temperature or theta E in the bottom left, horizontal wind speed in the bottom middle, and the horizontal wind direction in the bottom right. So the biggest differences between the moist tropical Saharan air layer and mid-latitude dry soundings are in the moisture and the wind variables. The mean Saharan air layer and mid-latitude dry profiles are drier throughout the troposphere. As measured by relative humidity, we see the blue and the blue line is significantly different than the red and the brown line. Water vapor mixing ratio, again, the brown and red lines are drier than the blue line, as well as equivalent potential temperature, which is not entirely related to moisture, but is significantly influenced by it. The red and the brown lines are significantly further to the left at any given altitude than is the blue line. So these profiles from the mid-latitude dry and the Saharan air layer sounding sets are much drier, especially above the surface. The Saharan air layer profile is distinguished from the mid-latitude dry profile primarily by its winds. So we have wind speed here, and we see notable differences there. And then we see wind direction here, and we see notable differences here as well. All 3 profiles primarily have winds out of the east from the surface up to about 500 hectopascals. The red, brown, and blue lines all are around 90 degrees, which is indicating that the wind is from the east toward the west. The mid-latitude dry, however, transitions to a northwesterly wind between 500 and 400 hectopascals, whereas the moist tropical and the Saharan air layer do so at much higher altitudes, 300 to 250 hectopascals. So this shows the mid-latitude influence in the mid-latitude dry profiles, where you typically have westerly winds above the surface. We see that closer to the surface in that profile than in the Saharan air layer or the moist tropical profile. Whereas in terms of wind speed, the Saharan air layer profile has much faster wind speeds in that layer of easterly winds than we see in the moist tropical and the mid-latitude dry profiles. This is associated with what we call the African easterly jet, and it's directly intertwined with the Saharan air layer. It's a unique feature of the Saharan air layer. We'll talk about that in more detail as we get after spring break. However, keep in mind that that's one of the key features that allows us to distinguish that air mass from the mid-latitude dry air mass. So this closes off our second lecture on tropical climatology. In our third lecture, we'll go into how diabatic heating can be used to drive tropical circulations.